Okay. So let's talk about your question first. So, let's start off with a simple one. We're going to go over a router, right? We have two flows going into the router, and it's going to be fair queuing. Or it's going to be first come, first serve. Regular queue, no unmanaged queue. Right? So, presuming these were both the same weight, right? And the outline is the same rate, so it's full and they're actually getting buffered. What does our queue look like in here? This is A and this is B.
A mix between A and B.
A mix between A and B. In general, there's a probability if you know, but in general it's a half A and half B, right? So if we have a queue, right, so A will arrive, B will arrive, A will arrive, and if there's some jitter or something going on, there might be a couple A's, right? But if you do it over enough, right, it's generally half. So we can say that this queue looks like this. If we add a third line in there, then, right, then it's about a third in general. So that's for fair queuing, or for unmanaged FIFO queuing. Now, let's say we're going to do fair queuing. What does that look like?
They don't have their own separate queues.
They'll have their own separate queues, right? So, however, while we conceptually think of it as it having its own separate queue, that's not really what it is. It's just a piece of memory, right? And so, in general, there's an algorithm that's sitting on here, and that algorithm in this case equals fair. So it doesn't matter, like, if we go back to the old one. Imagine you have A going in and B going in again, and A is at half the rate of B. What does that, in unmanaged queue, what's that look like?
BBA, BBA, BBA.
Yeah, it looks like BBA, right? Because the line rates are coming in, and in general, there'll be 2 B's for every A. So it looks like this, right? So, but in fair queuing, if the line rates are the same, it's A and B, right? What if A, just like here, is at a half?
Still the same.
It's still the same. There's an algorithm sitting on it, right? We conceptualize this in the class talking about it, saying, hey, there's separate queues, right? It's not really a separate queue, but in general, right, there's a managed queue on it. So if A has something to contribute, even if it's only doing it at half speed, then the queue looks like that still. Now let's do weighted fair queuing. So A equals 2. A has a weight of 2. What's our queue look like now?
2A, 1B.
2A and 1B, right? So we have 2 lines going in. The way I usually conceptualize it is I'll make a queue and I'll draw it out. Feel free to draw it. Make a queue, and there's A and B, right? That's fair. How do I make it weighted fair queuing? I double A's. So it's super simple like that. Let's move over here. All right, we got flows coming in. Actually, let's put. All right, so all the routers do unmanaged queue. right? All the traffic is exiting here. What's it look like?
So A, B, and E, and D and C are all inbound traffic?
Inbound traffic.
A, B, C, D, E. Right.
Any guesses? So we gotta compute this line, right? And we gotta compute this line.
The first line is just gonna be AB if it goes the same rate.
So it's A equals 1/2 of line speed, right? B equals 1/2 of line speed. Right? What's it look like here? Compute this line.
So A is gonna be at a quarter,
A's at a quarter.
B's at a quarter, and E's at half.
Yep. What about that line?
More fractions.
Right. D's at a third, C's at a third.
Yeah. So this is where it comes in, helping. This will help you if you just draw out the Q's. So what's our Q look like here, right? There's only 2 incoming lines, so it's half. Right? So it's A, B. So A would be A over A, it's 1/2, right? So in here, we have 2 lines coming in, right? Just 2 coming in to this router, 1 going out. So there's only 2 coming in, let's make it a half. Well, what does it look like? Well, there's A and B are coming in here. So this is A and B, right? And then for, since we divided this side in half, we have to divide this side in half, but it's only E on this side. Let's compute this line. There is 3. Our Q looks like 3. 1, 2, 3. So we'll have, let's label these 1, 2, and 3. So D and C are easy, right? Because they're 2 and 3, D and C. What does this one look like? Well, we already computed that. We know what it looks like. It's this, right? So it's A, B, E, and E. We have to divide that in 4 places, right? So now we have D's in 4 places and C's in 4 places. So our Q, we've divided up 12 times, right? So A is 1/12, B is 1/12, E is 2/12 or 1/6, D is 4/12 or 1/3, and C is the same 1/3. Now, same thing, let's do weighted fair queuing. We're gonna I'm only gonna give A a weight. So let's give A a weight of 4. Okay, so what does this queue look like? Or this line look like?
4/5 A, 1/5 B.
Well, let's see.
4 A's, 1 B.
So we divide it up, right, to A's and B's, right? And then A's, we're gonna put it in 4 times, right, amount of packets. So that is 4/5 A, and B is equal to 1/5. Let's just leave that one there. What does this one look like?
Do we still get priority to A?
Sure, A has a weight sitting on its packet, and we're not changing weights.
A3 Qs.
So we start out with, how many input lines do we have?
2.
We have 2. Let's start out with a queue of 2, just like before. Right? So, what does this packet look like?
You have 10 keys?
Huh?
You have 10?
Well, there's only 2 lines coming in. Right? So let's put our stuff there and then divide it up, right? So, let's just call this 2 and 1 again. So 1 and 2. So this is E, right? What does this one look like?
Or a B.
Huh?
Okay.
So right now it looks like A, B, right?
For each A, do we give it a weight of 4 again, though?
What do you think?
So it'd be 16 A's?
It would be 16 A's. Right? So we have 16 A's here, a B, and then 2, right? So this is 19, 19ths. Right? We propagate that all the way through. Now in a real network, weights get changed, right? Based on not actually a tag on the packet, because we figured out, well, we could just game that system, right? It's based on a field in the TCP header, and the routers are allowed to modify that field, right? And the routers adjust weights accordingly based on those fields, what their field, what it looks like.
Wouldn't it be 18? E would still be 1?
Huh?
Be 1B and 1E?
Well, no, so we messed this up. Hold on. So this should be 16 and 1, right? Should have used 2.
17.
Huh? So this is 17, right? This is also 17. So it'd be 16th, 17th, or no, 34th A, 1 34th B, and 17 34th A, or E.
So E's link would never, like how B's link went down because A had a weight, but E's link would never go down, it would still be half. I'm guessing the weight of A would never spill into E. So we get that.
No, we had it right the first time. 16 17th A, 16 19th A, or 18th.
There you go.
Yeah. 16 18th A, 1B and 1E.
Why A is 16?
Huh?
Why A is 16? We took its weight in the beginning. So this stage should just multiply 2 because we have 2 lines. So it'll be 8 points.
Well, let's just look at what the actual queue looks like, right? So in an if this was unmanaged, it would look like A, B, and then 5 E's, right? That's unmanaged. but in weighted fair queuing, the queue is forced to look like this. This is why we gotta go through these problems. I made this one too, your test one is not this hard. Weighted fair queuing puts an algorithm sitting on top of the queue to make it look like that, right? So it has three inputs, A, B, and C. A, B, or B and E are the three inputs. There's an algorithm that's sitting on the queue to make it look like this, right? So to force it to look like 4 A's, 1 B, and 1 E. Yes, sorry. When weighted fair queuing, the algorithm, so long as there's packets available, the queue is guaranteed to look like the weight. So since A has a weight of 4, so we have 3 different flows coming into it, and line rates don't matter, and that's what we missed the first time. Line rates don't matter in weighted fair queuing, or fair queuing for that matter, unless there's not a packet available. That's the only thing. So if the line is always full and A is always available, the queue looks like this. So let's go over it again, because I jacked that up badly. Algorithm sitting on top of here, right? That makes A be 4 times what all other traffic is, right? So there's 2 A and B, but A gets 4 A's, right? So it is 1/5 B and A is 4/5. If it was just fair queuing, then it's a 1/2 and a 1/2, right? Just fair queuing. Comes over here, what does our queue look like? Well, it looks like this. A, B, E, because it's fair. What does our queue look like down here? It looks like A, B, C, D, E, 1/5 each, because it's fair. Doesn't matter what the line rate is. Now, let's keep our queues here. Oh, I just erased one. This is fair. Let's weight it. So if we're going to weight it, all we do is do 4 A's. Right? So here we would do 4 A's. And here we would do 4 A's. So this would become 1, 2, 3, 4, 8. Or 8. So A through here is at 1/2, right? Everything else is at 1/8. A through here is at 2/3. Everything else is at 1/6. Right, and A here is 1/5, or 4/5, and B is 1/5. It's just write the queues, divide them up. Line rates don't matter in weighted fair queuing, or fair queuing for that matter. Just leave this here. Now let's go to your problem. We have a 4 megabit link coming in, and we have 3 flows trying to push at this. This number is bigger than 4, we're going to have a queue. So what's the first part of the question?
For each flow, what fraction of the packets it sends are discarded?
Okay, and for fair queuing?
Uh,
Or unmanaged queue?
Unmanaged, it says.
Let's do an unmanaged. So that means that unmanaged means that line rates matter. So we have 1, 2, and 3. Unmanaged, what does our queue look like?
1 from 1, 2 from 2, and 3 from 3.
So we have 1, 2, 3, like that, right? The queue is full. So we're going to start dropping packets. What percentage of packets are we losing?
1 6 1 2 6 2 and 3 6 3.
Yeah. So we're losing 50% of these ones, right? We're losing 33% of these ones in a third. And we're losing a sixth of these, right?
Wait,
All right. Is there more to that question, or is that it?
I mean, there's B, C, D, and E. You want to go through every one of them?
Well, because it's going to matter.
All right, let's do it.
So what's B?
Yeah. For each flow, about how many packets does it have in the queue?
For each flow, how many packets does it have in the queue? Huh?
300 times that percentage.
300, yeah. So 300 for, so it's 1/6, right? 1/3 and 1/2. Is that right? And so, B times 300, simple math, right? What's C? I know it gets more complicated.
Oh, part C. Now suppose the queue at the ISP is replaced by 3 queues that can hold 100 packets each.
Oh, all right. And these are all 100, right?
Yep. And
Okay.
all the weights are 33, so it's weighted fair queuing.
Weighted fair queuing. Okay?
All weights are 30.33.
Which is the same
Fair
as
queuing.
1, right?
Yeah.
Served round robin style, or however you want to look at it, right? So it's going to be served round robin. So we have 3 queues. What do they look like? Are they? So this one is 1s, right? This is 2s. This is 3s. They're being served round robin. What does the first queue look like?
It's 50% full.
So you might run into problems. If you ever think a queue is half full and you're not actually looking at a state of a queue in an instantiation, if your generalized queue is either full or it's empty. There's never a half full.
Oh.
Because the question is one being dumped fast enough to empty it? What's our data rate? So our data rate is 4. This is being served round robin. So each queue is basically getting what?
4/3.
4/3 of a megabit, right? What's this queue look like? It's empty. It is totally empty. What's this queue look like?
Full.
It's full, right? And what's the 3 look like?
Full.
Full. Now, what was the question?
Oh, the first part was, so part C. In this case, what fraction of packets are discarded from each flow?
So this one's easy, right? 0. 0%. This next question is harder. So there are two ways we could go about it. What is the data rate on these two queues if this one is empty?
Would those data rates consume the other extra 30% that the first one doesn't need?
Yes, they would. They would in fact consume the other 30%. Right, because this is only going at 1. Right, so what's these look, what's our combined data rate here?
3.
3, right? So this is going out at 1.5, and this is going out at 1.5. So what is it, how many packets are being lost?
25% for the first one.
25% for the first one. Why?
Because it's at 2, and so if you can only hold 1.5, 1.5 divided by 2 minus 1. Yeah, 1 minus 1.5.
1 minus 1.5 over 2, right? 25% being lost. What's this one? How many being lost here? 50%. Now, the D is the kicker.
D was how many packets does each flow have in its queue?
Huh?
D was how many packets does each flow have in its queue?
Okay, that's actually easy. 0, full and full, right? 0, 100, 100.
So E then was now suppose weights. We have weights 0.2 for the first flow, 0.6 for the second, and 0.2 for the third. And in this case, what fraction of packets are discarded?
Okay. How are we going to go about doing this?
Multiply the weights by the total output.
So we can we do the output side. So you can do the input side or you can do the output side, doesn't matter. So they start asking how many is in each queue then. But so 0.2, 0.2, and 0.6, right, means basically that it is 1, 1, and 3. So what's the, if we do the output side, what's the output for this?
0.8. Wait, no.
So the 1, 1, and 3 equals 5, right? So here we would have 1/5 of 4 megabits per second. Here we would have what?
3/5.
3/5 of 4 megabits per second. And here we would have 1/5, right? So you could do it that way, or you could make 3 of these queues. But essentially the math is the same, right? Because you're just going to have to add it all together anyway. So, 1/5 of 4 megabits per second. So this is 4/5 of a megabit, right? This is 12/5 of a megabit, and this is 4/5 of a megabit. All right. So, what do the queues look like? Which ones are empty? Which ones are full? 2 is empty.
Would the remainder 2/5 of that flow spill over to the remainders?
Sure.
Okay.
Case 1 would be empty 2.
Huh? So, yeah, let's think about this, right? So this one is empty. right? Because it's only filling at 2, right? So if we subtract 2, we have 2/5 left over. That will be evenly distributed to the other 2, right? So then you get 1/2 because evenly distributed, and there's 2 cubes left of 2/5, which is essentially 1/5. So this is 1, and this is 1. Amazingly, the numbers are easy. What's this cube look like?
Empty.
It's probably empty. Questionably, this is where the one thing where it's like, is it empty or is it full?
Based on jitter.
It could be on jitter, it might be full, right? But it might be empty. But really the answer is, question. You could just probably treat it as empty because it's being emptied as fast as it's being full. So while the actual state of the cube is in question, right, it is essentially an empty cube from a computation standpoint because everything that's being put in is being put out. Nothing's being dropped. What's this one look like? It is full. And whatever a packet's being lost. This one's being emptied, right? Or something at least approaching 0, right? This one is definitely 0. And what's this one?
Percentage lost is 60.
66, right? 2/3. So there's a question like that on the test.
Oh, man.
Why do we have OSI layering model? Why do we do layering?
To make life harder. Another answer.
It's actually the exact opposite of that, to make life easier, right? For 2 reasons, right? It makes it more manageable pieces, and it allows you to change a layer without jacking up any of the other layers. Loose coupling, right? Be able to understand the syn-ac of a TCP handshake. Know the difference between congestion control, flow control, traffic shaping, all that stuff. General, you don't have to define anything, but if you're given a definition, can you pick the right one?
Is it congestion control, flow control, and what?
Traffic shaping
Traffic shaping.
and smoothing. How do you calculate the length of a packet on a network? Do we remember back then?
For the ruler.
A really long ruler.
2 times the bandwidth delay product.
Isn't it just
Overthinking about that, huh?
Isn't it just a bandwidth delay product?
But a packet has, how do you, so yes, if you're going to architect a packet length, it is the 2 times the bandwidth delay product, if you're going to architect it. If you're given a network, if you had a 100 megabit Ethernet, right? Could you tell me if it's 100 megabits per second, and that includes the entire packet length, what is the packet length for a 100 megabit per second network?
You know the length.
Huh?
You know the length. The length of the network.
No, you don't.
Oh.
So how many packets are being put on the wire? 100 million a second, right? So how long does it take to put 1 packet on the wire?
Length of a second.
A 100 millionth of a second, right? And what's the length of that packet? 1/100 millionth times whatever the propagation is, right? So if it's wireless and it's in air, it'd be times the speed of light, right? If it's over a wired medium, it'd be about 2/3 of that. So there is a relationship to the whatever speed your network is versus the length of your packet on the wire. Be able to do the fun micron. If I gave you a distance between two things, the distance between 2 points in a bandwidth spectrum, right? So like, let's say 50 and 60 microns. What's the bandwidth of that? We've done that before. CRC division, which should be really familiar, really familiar. How do you figure out how many computers are in a subnet?
Ping speed?
There you go. Possible computers. How many IP addresses are in a subnet? How do you figure that out?
Look at the subnet mask.
Yeah, but you're given the subnet mask. What's the actual? How do you actually figure that out?
Take 32 minus the subnet mask, raise it to the power of 2.
So it is 32 minus the cider, right? Raise it to the power of 2.
Oh no, the other way, 2 to the
Yeah.
power. Yeah.
2 to that, right? What if you're given this? How many computers are in that thing?
Gotta figure out the binary.
So what's this one?
It's a /15.
Is it a /15?
Should be right. So go like there. 130,000.
So what is this one?
/8.
That's a /8, right? And what is this one? This is a /16, right? So is this one closer to that one or that one?
Good point. It's a /9.
It's a /9. Remember, 128 is a direct power of 2, right? So if it's a direct power of 2, this is this is 8 ones, right? And this is 1, and then all zeros. It's a /9. But your equation still applies. Yay! Feel free to use the internet to find, like, what routes are where when you're given an IP address and it's going where to where. Feel free to use that. There's an IP calculator out there. I am not worried about you figuring out how to do IP calculations by hand. What I am worried about is you being able to say, hey, I'm given an IP address, which route does it take? Remember, there's overlapping, right? And it's the most specific. Right? It might be able to go out one, but the first thing you need to do is figure out which the one is more, like, rank them in order of specificity, right? And then if your IP address fits all 4 in there, you pick the one that's more, right? Okay. remember that doubling, quadrupling 100 times faster or 1,000,000 times faster doesn't necessarily always make your connection faster, right? Because it's always the long pole in the tent, right? So if you have very small packets and you have very long delay, upping your bandwidth might not help. Be able to calculate that. So if you're given some amount of data that's being sent, there might be something missing in this question. Oh no, there it is. It's over a line, new line. So if you're given an amount of data, calculate how long it actually takes there to get there, right? Is it delay limited? Like, can you put the whole thing on the wire before it arrives to the other side? If you put the whole thing on the wire before it arrives to the other side, it's delay limited, right? If you can, if you're still putting stuff on the wire by the time it hits the other side, then you're bandwidth limited, right? And just you can figure out mathematically what the capacity of the line is, right? Versus your data, and that is the tipping point. If you were given a 100-kilometer long line, right, is fiber, so fiber is at 2/3 the speed of light, then and you were sending 100 bytes across it, right? Where's the tipping point for bandwidth versus delay? It's probably easier to do 200-kilometer line. How long does it take for a byte to get across the line?
1 second.
Or a bit?
1 second.
No, it should be one microsecond, right? So 2 times 10 to the 8th, or 2 over 3 times 10 to the 8th. No, it would be, this is 2 times 10 to the 8th because it would be 2 over 3 times 3 times 10 to the 8th. So 2 times 10 to the 8th is the delay, right? And then if you're sending it to 100 or 200 kilometers, then that is 200,000. So that is 2 times 10 to the 5th. So it's 1 microsecond, right? So it takes 1 microsecond to get across, right? So if you were sending a 100-bit packet, then a 100-bit per second line would fill the network, right? That means that by the time you put the last bit on, the first bit has just arrived. Right? So you can find where those things are. Okay. And then that question. And funny enough, basically that question we did before. Remember, a FIFO queue is dependent on line speed, what is coming in. A managed queue has 0 to do with that, so long as that is full. So if you can presume everything is being full all the time, then it's simply write down what the fractions are. Over here, since we actually had packets, right, then we had some spillover from stuff that wasn't full. Right, so it changes we start out with how we did on this side, basically putting our queues down. This is what our queue is going to look like. but we had actual numbers to say this one was drained. And so it is, some of that bandwidth is going to the others. But in general, you look for which one gets drained first, you allocate to the rest, right? If any other are being drained and there's leftover, you allocate to the rest. If any other is being drained and there's leftover, allocate until there's nothing left over. And then that is your state, and then calculate your numbers.
Is that also true in the managed queues?
Yeah, we did weighted fair queuing over there, managed queuing. All right, and that's the test. You gonna do your presentation? All right.
One person said to me that window sizes were negotiated during the TCP Synapse handshake. I told them they were wrong. Was I wrong?
Okay, yes.
So, well, it depends on how you. So yes, window sizes can be negotiated in the TCP handshake, but it's not passed in the TCP handshake, right? It's part of the. Okay, I try a big packet, right, and it doesn't make it, and you get ICMP responses back from the routers, right, until you get one. The very last one could be your host that says that size is too big for me. I don't know why that would be, but possible, right? And then they would send an ICMP back to it smaller, but it's not technically the handshake, though. You would discover it then.
Okay.
Does that make sense?
Yep. Got it. But that
So window sizes for flow control are negotiated in TCP itself, but that's ongoing.
Yeah. Okay.
That is this machine?
Sure. Yeah.
Because this one.
Well, it depends on, do you want to use laptop or?
Press space bar.
It's not over there.
Yeah.
Yes.
Running your P's and Q's, that's awesome.
Hello everyone, sorry my voice is not very good today, my throat is sick. And I want to first apologize for the late. I've been through a lot with my thesis, but finally we just last Friday decided to propose and defense this week and next week.
Congratulations.
Thank you. So I'm gonna present my critique paper, which is about the detection the widespread weak keys in the network. The objective is to search for to search for a lot of keys that could be vulnerable on the internet, especially on the TLS and SSH. Analyze that collected keys and find what's wrong with them. They use a very good technique that enable them to collect a lot of keys from internet using the map scan from the Amazon EC2. They could collect 29. They scan 29 million hosts on the HTTPS and 23 million hosts on the SSH port. By using the handshaking on the SSL, they could find keys for 30 million of the HTTP hosts and 10 millions of the port 22. So then they went to manual analysis to find what's wrong with these keys. The first thing they noticed, more than the half of the keys are repeated in the in the HTTPS. There is about 13 million keys, and just about 6 million are distinct one for the RSA, and only 6,000 are distinct for the DSA. And the same year, just less than the hub for the RSA and the DSA. So they went to investigate what's wrong, why there is a lot of repeated keys. They figured out that there is non-vulnerable reasons for that repeated keys, and most of them for big corporations that share keys through certificate, since they have a lot of services. But the vulnerable ones, basically, most of them for the default keys that comes with the embedded devices. They found also repeated factors for the modules. Although there is two different keys, one of these factors can generate, but knowing one of them can reveal the private key. Using this algorithm, they calculate the GCC for pair of moduli that share one factor. They could do that with algorithm, this one here, and there is a sophisticated math behind this, but they implemented it on the Amazon server. It talks about 1 hour and costs less than $5 to get about more than 2,000 prime factors that use to compute over 64,000 TLS host private keys. There is also repeated VSA signature. The same issue here. There is the K, which is the ephemeral key. This is a temporary key that generates the private key X. So if we know this key, we can calculate the private key. How we can know the key if two messages share the if there is two messages signed with two signatures, and the signature use the same key, the R1 and R2 here must be equal. So we can calculate the K if we know that one of these signature used to sign the same the same signature used to sign two messages. So they collected more than 4,000 signatures, used the same keys, and they used it to calculate more than 100,000 private key for the SSH host. So they went to investigate the problem, why there is shared keys in all cases. The Linux urandom is used in most of the devices that investigated. So in Unix recommended to not use this library for embedded systems, but most of the embedded system use it. They need time of the boot and keyboard, mouse, disk accessing time to generate entropy that's used to generate the keys. So in the embedded system, there is just one time the device boot, and that's it. There is no keyboard and mouse in an embedded system, and most likely there is no disk access. So the pool here will be very poor, and there will be very poor randomness. From this poor randomness, we could see a lot of shared keys. So to solve this problem, they brought advices for developers and certificate authors and the users. For the developers, they recommended to use extra piece of hardware to enhance the entropy of generating the keys. And for the certificate authorities, they suggested to test the repeated keys factorable and investigate the weaknesses in their keys. For the user, they recommended to don't just use the embedded device with the default key. They need to regenerate the keys. So the strength of this paper, actually, in my perspective, the paper is very strong. There is a huge data set they could collect it using naive implementation. They investigate everything and they came up with some recommendation and mitigation for user, developer, and the certificate authorities. The weaknesses, I couldn't see big issues except that the algorithm that they use to calculate the GCC, the GCD, is very standing behind very hard math that they didn't even mention. They just mentioned the source and that's it. The future work, they can apply the same method they use to another type of cryptography applications, such as the Diffie-Hellman. I read about the ZMAP, which is, I just saw a video on YouTube explain the scanning with the ZMAP. We cover a bigger area with less time. So this is what I have today. And questions, please.
Did they say if using dev random would have been better than dev random in those
What
embedded
is it?
cases?
Dev random.
Dev random versus dev random. Did they mention that that would be better for the embedded cases or no?
Actually, I'm not familiar with this library. What I know is you random need the physical movement or some time rebooting to generate the entropy. I didn't see the paper talk a lot about the other. They talk about if there is extra hardware could be used for the embedded system to generate the higher entropy.
Thanks.
There you go, 1% of embedded devices. You can derive their key.
Boom, your Sensi homes.
That's right.
No, my coffee maker.
Right.
That was probably a lot of the electric grid as well.
So, I don't know if they still do it, but one of my friends was looking at like Colorado Springs Utilities like online portal,
Uh-huh.
and they passed his username and password in plain text in a URL query.
That's
What?
awesome.
Sweet.
So,
Yeah.
Oh my god. This is why I will
Fail.
have a job for a while.
That works fine as long as please don't read that.
That's
yeah,
right.
plain text too, yeah. You can't get any weaker than you already are, so.
So all you have to go after is the web logs and you can get everybody's password and nobody ever reuses passwords.
Question for you,
Or like when the OPM incident happened, no one ever says like, oh, the OPM incident happened. And also Ashley Madison, oh, you know, the rights or website thing? Cortland accused you? No. Blackmail? Right, so now you have the list of cleared individuals from the US government and a list of blackmail sources.
In the middle of that Venn diagram, sweet hater.
Right, exactly.
So we had
Just boggles my mind still.
I don't think
Really
a lot of
think
things
it's
are.
I didn't actually subtract.
One of the fellows is up.
Yeah, we subtracted 2 from this to get the 2 bits, and then we distributed each or half of that to each one.
Just so.
And use that to determine that this one was the right. Was that 1?
شايف شفت عدد المشاهدات
So this one is being, this one's being drained at 4/5 or 3/5 unscored, right? Which is 12/5.
Yeah, it's taking out.
Is being filled
Okay.
at 2. It's how fast it's being filled. That's the problem. So that 2 is that.
بس هو بصير أنا بشوف
Okay. So it's trying to drain at.
So it's draining at 12/5, but it's only being filled at 2. So there's 2/5 left over, which is why it's.
Okay. That makes sense. Okay, thank you.
It's still not recorded, by the way, which is a good thing for me.
Okay, on question 10.
Still recording.